The difference of squares formula is a very underrated formula. It's one that we're told to memorize and learn, but there's such a beauty behind it. It's really a shame that we don't talk about it more. The difference of squares formula looks a little something like this. It says if I take a squared, where a is some number, and I subtract b squared, where b is some number, that I can write this entire thing using parentheses, where I have a minus b in the first parenthesis or a plus b in the second parenthesis. But what does this actually mean? After all, I don't see a square, at least not the shape of a square. Should we actually be able to do this with real squares? Well, let's try. I'm going to draw a square. How big is my square? My square is an a square, which means it has a side length of a and another side length of a. This is an a square. And I'm going to try to take out of this a square a b square. And I'm going to draw that in green. So I'm about to chop away a square right there. How big is the square? It's a b by b square. So we're taking away one square from the other. We're literally differencing the first square by another square. We're doing a difference of squares. So that's where I've chopped away, and I'm curious what we have left over. Well, as it looks right now, it's not immediately obvious. Maybe I'll break this into chunks and I'll say that what I have is the equivalent of a large rectangle on top and a smaller rectangle underneath. Do we see how this is really me just having the same amount of paper? I've just cut it into two pieces of paper. Well, how big are each of these? This part here is A. I know that for certain because it carries over from the other. This part here, how big is it? It used to be A, but now it's B less. So I guess that's A minus B. Okay, interesting. What about this one down here? This has to be B high because that carries down from the first picture. And how big is this side? This one has to be, well, also, it used to be A and now it's B less. So I guess that's A minus B. So that means all in all, this entire piece is B times A minus B. And this piece up here is A times A minus B. Well, then how big is all of this? It's A times A minus B, and it's B times A minus B. But shouldn't there be a better way to organize this statement? I mean, after all, A minus B is appearing twice. Let's factor it out. Let's use that as a base by which to organize everything. That'd be A minus B groups of A plus B. Now, if that feels weird, really what we're playing with is, again, right here in this picture. So we've got A minus B as a common side length. We see that right here and right here. So let's grab these entire rectangles and let's do a little bit of rearranging. Let's grab this entire thing, grab this one right here, spin it. So I'm actually going to just draw it again. So I'm going to take this entire thing and I'm just going to spin it so that now the B is on the top and the A minus B is on the side. So I essentially have A minus B now nice and lined up. If I stack both of those together, I can describe this entire remaining shape as A and B long and A minus B tall. Well, that makes sense because it's exactly what we showed in our symbols up here. So the difference of squares literally means that I'm about to take one square, cut away another square, rearrange them to a common factor, and then I can describe it all in terms of a rectangle again. This is what the difference of squares is. A squared minus B squared is A minus B times A plus B. The difference of cubes is the exact same idea as the difference of squares, except now we're literally going to start with one cube and then take away another one. So here I've got a picture of that, so I don't have to draw it. It's a large A cube, and you've taken away a B cube out of it. And I'm curious about how much is left over. Well, instead of looking at it all at once, let's just see if we can't kind of pull it off into a couple of different chunks. So I could look at this entire thing as being just a little rectangle part that's still up at the top, a larger rectangle part that's in the back, do we see that? If it helps, let me draw it in a little bit. Down the bottom, you've got this rectangle right here. So this is all this purple, is the purple right here. This right here on the top is a chunk that I'm going to grab and move over here. And then everything in the back here is this one here. Let's begin to describe the dimensions. This one is an A by A by, it used to be A, but now it's B less. So that means A minus B. This one over here was something that used to be, or is B tall. It used to be A wide, but now it is B less than that. And it is B in depth. This one back here was something that used to be A wide, but now it is B less than that. It's A wide up here, and its height is B. So if you want to describe the size of all this, we're just talking about lengths and widths and heights all being multiplied. So this first one here turns into A minus B times A times B. This next one here just turns into A minus B times B times B. And this one down here just simply turns into A minus B times A times A. Which means that if you have taken a cube and you've taken away another cube from it, the components you have can always be looked at as A minus B times A plus A minus B times B plus B plus A minus B times A times A. Now in the symbols, we might be able to look at this entire thing and say, look, there's an A minus B that's common in everything. Let's factor it out. So sure enough, let's talk about this in terms of just A minus B groups of everything that's left over. We have an A times A left over, or an A squared. So that's these two. We have a B times B left over, which is a B squared. And we have A times, oh, did I miss one? I did. This one should have been B. There we are. So this would be an A times B in the first. A times B, a B squared, and an A squared. If you rearrange this a little bit, you'll get what's normally referred to as the difference of cubes formula. A minus B times, and we'll make this alphabetical, A squared, AB, and B squared. But what is it that we're doing in this common factoring? We're really just looking for a common side length. Notice that this side length here, this side length right here, and this side length right here are all the same. Now, a very similar approach can be done if you do the sum of cubes. Now, I'm not going to do this one geometrically, but the idea is no different, that now what we're going to be doing is going to take one cube and add it to another cube. So in other words, we're going to be stacking one cube on top of another cube. That means that we're going to be getting some kind of shape that turns out like this, where we've got a cube on top of a cube. And after you do all of the exact same thing, where you break things apart and you look for common side lengths, you can find out that that's actually going to come out to the formula of A plus B times A squared minus AB plus B squared. This is the sum of cubes formula. So you have the difference of cubes formula and sum of cubes formula that just comes from simple factoring. Now these can become a little bit difficult to remember, especially on a test, so there's an acronym or a shortcut, a mnemonic that we use to help keep track of what these are when we're working through problems quickly. And that acronym is SOAP, S-O-A-P. And it works with the difference or sum of cubes, and what it stands for is same, opposite, always, positive. What it means is that if you are starting originally with the sum of cubes formula, which is A cubed plus B cubed, and you'd like to expand it, then sure enough, you can do that. And remember that the formula we're playing with after that has the same sign first, the opposite sign next, and then the last one is always positive. For the difference of cubes formula, that would be where I take a cube like A cubed and I subtract B cubed. That's going to be the same Sign first, start with a negative, and I have a negative that first appears, opposite, which is positive, and then always positive for the last one. And so this is a nice, easy way to remember the formulas for the sum and difference of cubes, but it's really, really important to recognize that when we talk about differencing cubes and summing cubes, there's a story and a picture that goes along with it, so that there's actual real meaning behind the math that we do.